Good afternoon to everybody. This is the second part of this masterclass devoted to design of building and a structure against explosion. It's just the second part. We are dealing with a structural response by means of simplified method. We will say something about project and structure, and the relevant standard is very important in this subject. A bit about typology, and especially when the building or the structure are made of steel, concrete, or composite. And a special case and a special situation, we have to take care about the roof and the facade, and at the end, the common reference belonging to the first part and the second part. Well, the structural response by means of simplified method is, as you can see in the bottom, is to simplify the action we deal with in the first part by means of a maximum pressure and a duration in relationship with the response of the structure. Simplifying, the structure have a maximum resistance and a displacement coincidental with the linear behavior and an excursion in a plastic branch. So this the relationship between pressure and resistance, time of duration, and period of the structure lead us to this concept, the concept of ductility, the relationship between the maximum displacement in the response and the linear one. This relationship is in some sense is more or less the damage that can suffer on a structure. It's important to insist to point out that the structure we are going to deal is just a single degree of freedom, and a structure, a building, is a complicated and complex situation and has a different behavior depending on the load. But when we deal with an explosion that mainly is an horizontal force in the case of facade, in the case of a normal and ordinary building, the general equilibrium is this equation that appear in just as number one. The effect of damping in this equation is neglected because the duration of the load is very short, and consequently the energy in this that can dissipate due to this phenomenon is also very small. So the equation become the mass multiplied by the acceleration, the resistance, and the force. This is an equilibrium dynamic because the force is changing along the time, and on the other hand, the resistance, and on the other hand, the acceleration. I mean, we can expect to obtain the reaction as a classical manner by balance the total forces. Part of the forces in this situation are dynamic forces. Well, we have to take into account that one thing is the behavior linear when the action is under the maximum resistance of the structure, and another one have superate. So to convert a complex structure, an actual structure, into a single degree of freedom, there are some transformation factors. One is to convert the total mass in an equivalent mass, the stiffness of the structure that depend of the forces and the variable forces in one equivalent due to an horizontal pressure in that case, or vertical in case of a roof, and also the equivalent forces in the sense of force and effort. So the structure is converted in this constant, but the mass and the stiffness and the force. These transformation factors are obtained by balancing different concepts. The first is the load factor. The load factor is something that relates the external work of that produce the explosion by the external work, the energy in a single degree of freedom. The mass, for instance, the mass in the single degree of freedom is an equivalent mass that is an abstract of the total mass of the building, and another is well, of these things depend about the law of deformation, the so-called, here is self-value. Self-value means autovalores, that in English is agent values, the agent values of the system. Well, when you have changed the equivalent mass and the equivalent stiffness, we can calculate the period of this single degree of freedom, the period of the structure we are going to deal with. This is usually very close to the first period of the structure, but not necessarily. In Annex A, at the end of this presentation, there are a sort of abstract about the most common system for beams especially. You can find this also in the first references, reference 1, 2, 3, and especially the reference 8, the introduction to the system, the dynamics structure by Biggs. Well, the design graphics for an idealized load at the end is like this. We have a spring, we have a mass. These are subjected to a force, and the force has this simplification we deal with in the first part. I mean, a maximum force is the typical situation for the detonation in an explosion due to NTN, and a duration that is a part of the usually of the period of this structure. Another point very important is the area of this triangle. This is the momentum, the impulse is the area of this. Well, there are two kinds. We have already said that there are two kinds of response. One response is elastic. The elastic response is only when the forces are very, very, very low, because this supposes that the structure remain linear. Anyway, depending on the shape of the force, this is the typical detonation. Another could be deflagration, but in this figure we have the two ones. We are dealing with the first, with the worst. So if we take into account the duration of the total duration of the phenomenon divided by the period of this equivalent system, we have this number, and we can obtain an equivalent static equivalent, this dynamic load factor. This number this value resume the effect of this explosion in the structure, multiplying the maximum value. So for linear behavior and a long duration, the maximum dynamic load factor is 2. When we exceed this proportion, the response is in the plastic field. In the plastic field, we have to consider the response of the structure when the structure has reached the maximum resistance. But the structure that are designed just to resist this sort of actions have ductility. Ductility is the ratio in an explosion, or even in an impact, or the same concept for seismic forces, is the relationship, I insist, between the maximum displacement and the elastic displacement. Is a proportion on how damage has produced the phenomenon, because if the maximum displacement is superior to the linear one, when the actions disappear, so the rest remain a deformation, and this deformation suppose a sort of damage, more or less, of the structure. In this graphic is very important, it's crucial. We will spend some time in this. For instance, in this triangle, this is only for triangles of this shape. In this triangle, we have the maximum force that act at the beginning. This is P, and the structure has this diagram. This diagram, the relation between two is this number here. For instance, 0.5 means that the resistance of the structure is half of the maximum force. This is in this intermediate color. This is this curve. So the other point is the duration of this phenomenon in relation, the relative between this duration here in the abscissas by the period of the structure. Well, if this duration is long, this is the worst, it's a bad situation. But imagine, for instance, we have 0.5. I mean, it's the half period and half resistance. In that case, the result is in this point, and if we advance to the left, we reach the damage. We reach the relation between the maximum displacement at the end of the phenomenon divided by the linear one. When we have, for instance, a very big structure, a very resistant structure that resists a lot, well, perhaps on a short duration, this is less than one. That means that there are no any damage. The maximum displacement is less than the linear. But this graphic so is interesting just in the middle, in this sort of situation. And this is relating the duration of the process, the action. This is the total duration in proportion of the duration of the load, and this is in proportion of the period. And this is like in the other situation, what kind of a structure we have. This, for instance, 0.1 means that the resistance is only 10% of the action, and this means the one is the same. For instance, here is the double. 0.5 is the double of the when the force, the action, the exterior is bigger than the resistance. Doing this, we can construct this sort of diagram, very useful in design, about pressure and impulse. Consider that here not only is important, is something that are connected, the force and the duration. Just the product of the force by the duration divided by 2 is the impulse, the momentum in English. So with different impulse and different pressure, we can reach the damage. This damage is a combination of both. But well, if the impulse is very low, I mean, we are in this part, it doesn't matter the pressure, because the dynamic load factor will be less than 1. We haven't any damage. And on the other hand, if we have a very little pressure and a small value, so it doesn't matter what is the value of the impulse. They are not damaged at all. And this is the maximum, the 10%, is when just we consume all the ductility allowable in the structure, and this is an intermediate situation. Well, it's important to take into account that there are several situations of several modes of failure. For instance, in the typical one, the flexure, when we reach the plastic moment, the plastic bending moment in one beam, and another is when we reach the shear in an extreme, in a reaction of a beam. So there are situations when a column or a beam can failure by both things or one of these. So it's important to develop these different curves. In general, shear and could be flexural, but for instance, in columns, it's also important the axial loads, or even though the lateral buckling, torsional buckling, depend of the design. Well, another utility. Well, we haven't enough time to explain all these things about explosion, but another very important is the effect in the human body. There are different mechanisms and different vulnerability in the human body, and well, this is very useful in order to establish the situation of any building, of the distance between the explosion and the situation of people in a building, in order to prevent and to consider, to take into account if it's important to protect or not. Well, a part of this, that very useful graphics, there are direct formulas taken from this manual, the manual 42 of the ACE. One is when the impulse is very little, and so we have this formula, this direct formula that take into account, like similar in the graphics, we have the duration and the period, the force that acted divided by the resistance, and we can obtain a number of the ductility. This ductility problem will be if the design and the detailing and the structure can actually have this ductility or not. When on the other end, when the duration is very large, it depends especially about the relationship with force and resistance. And for intermediate situation, the more complicated and useful, this is a very valuable formula. But we have to use this formula by trial and error, step by step, considering the here tau is the ratio between duration and period, and suppose a ductility and calculate the ratio between forces. We try different ductilities at the end when we obtain just the actual quotient of these forces, and then we are sure that we have obtained the response. Well, in this part, we are going about speak something about the building topology. The building topology is very important to distinguish between the situation when we are dealing with an existing building, or we are doing a new design. Well, a conventional structure not prepared especially for explosion can resist, for instance, a warehouse, something about 6.9 kilonewton square meter. Some more or less is this figure, one PSE. The building suitable for expression can resist a lot, but needs some requirement, especially in order to obtain a high value of the ductility. Well, another advice: unless the direction of advance and the force, the pressure act about one facade, if we are not sure about the situation of the point of the explosion, is better to consider that this force can act in every facade. Any facade, any direction of the building had been prepared just to resist this. Here in this figure, we have this relative position, and we can see that in plan this round shape is an advantage, because only a part of the facade is affected, and when we have another part of the building behind the first one, we have a minimum effect. Another point is unsloping in the facade and reduce the direct forces. These are advantageous situations, but difficult to construct. On the other hand, shape that accentuate that is the worst situation is we have situation like this, because the reflecting values are very high. I mean, in that case, we can use the simplified method. Well, about warehouse made of steel structure, they are very useful, because in a lot of industrial facility we have warehouse and buildings, industrial building in the surrounding area. Well, they are in general designed for ordinary conventional loads, like the weight, the bridge crane, wind loads. But it's important to take into account that as much margin we have against conventional loads, more good will be the behavior. And to achieve a blast resistant design, is recommended to have a little separation and a small separation between frames. Is the typical structure is based on frames, so 6 meters or less is better than to have 12 or something like that. Well, the connection, especially in the bottom, must be fixed and reinforcing the base plate adequately. The purlins, strap and brace must be symmetrical, and the cladding and the enclosure have to be very overabundant. I mean, to have a big margin about fixing and connection, and take care especially of the investment or rebound, because the force and the displacement and the force can change of sense of direction. So it's very important and advantageous to have a facade made of prefabricated concrete or reinforced blocks walls with reinforced concrete. Well, in a conventional building, we can resist external pressure about 20 kilonewton square meter. Another point is building, very similar to the we have dealt before, building without an intermediate force. Well, in that case, it's an advantage to have the frames in both directions, and especially use the roof as a diaphragm. So the exterior walls can play a role of diaphragm and bracing all the whole building. And if you take care about the doors and the window, we can reach about the double, about 47 kilonewton square meter. And this is a special type. It's important to consider the bunker type buildings. This is very often, this is the building that is designed very close to the explosion. For instance, in a harbor, in a port, near the boats where or the tanks where can explode. Here, the rounding corners, finishing. I mean, due to the fact that when we have fires and radiation, is very useful to construct this also in concrete. So concerning the spalling that happened when we have an wave that came into the concrete and change the direction and produce tension, compression and tension can produce the spalling. So an advantage is to have a sort of shield, interior shield, in order to avoid fragmentation and spalling in the upper part. This is also very useful in nuclear power plants because the interior of some buildings related to radiation is in depression. So the tightness is very important because in case of any failure, the exterior air enter into the interior, not on the other sense. So this shielding, this liner avoid the spalling of the concrete. The materials we deal is concrete, steel, and composite, the sort of mixed structures. Some qualitative differences between these materials are important. Steel structures are more slender, are lighter, and are more ductile, and usually offers a big ductility when we avoid a premature, preliminary, very early failure due to buckling or any instability. So it's recommendable, is necessary to design with the so-called section class 1 or class 2. In general, I repeat, this structure can withstand greater deformation. Reforming concrete are more stiff, more rigid, but has an advantage. The shear, torsion, and the efforts can calculate separately the reinforcement, and well, sometimes it's easier for the point of view of the calculation than the steel. But on the contrary, the detailing is more complicated. A good performance on a structure made of concrete, that we will say afterward, needs to be very laborious work in the drawings. On the other hand, I insist about rebound effect, the chain of deformation in the deformation is very important to take into account the reversal of forces. I mean, on the contrary, a conventional calculation here, the forces are not always in the same direction. This point, steel structure, property of the material depend closely of the rate, the velocity of deformation. This is a very useful figure because the quasi-static, this is the strain value in the inverse of a second, and consider that an earthquake is a problem. It's very quickly, but more is the impact, and the most important is the blast. The duration at milliseconds, and especially in relationship because the period of the structure is something very low. These are values that, in order to enlarge the properties of the yield point at the resistance, in that case, the Foucault format and for conventional steel. In the petrochemical facility, this standard also include an amplification due to ductility of the material local. I mean, is the stress increase factor. We have both. We will reach the situation where we have calculated the deformation, the maximum deformation, the x sub m, the maximum deformation, and the relation with the linear is this mu, this ductility. So here is important to take into account how is the limit of this deformation, and we are in hand of the relevant standard. In some references, depending of we are beam or we are frame, and depending of the category, this is the more light, this is the more important, the high category. We have deformation in the sense of angle and ductility. And well, we see we have reached 2 degrees and deformation of 10. I mean, ductility of 10. That means 10 times the maximum deformation. And they take into account this. This is the ductility in order to lateral deformation. In the last when the failure happened, we can admit the height of the building divided by 25, something very, very extreme, very important. Of course, at the end, the structure has suffered a ruin, but have coped with the requirement of to resist and to defend the properties or even the people. Here is the figure. This is the behavior in the plastic range of the structure. So to take a good knowledge about plasticity, because this is similar to this process is to perform a pushover, a progressive calculation of the deformation, substituting this point by plastic hinge and calculate step by step is the so-called pushover that we perform very often in seismic design. Here we have the another references about ductility and angle depend of the structure, the element type. For instance, we have beams, purlin, co-formed is not so ductile, and plates. Plate is the more suitable. And here also the sideway limit for frame. We have a lot, the high divided by 50, divided by 35, or the high ductility is divided by 25. This is the rebound. The rebound is the relation about the negative force in proportion with the maximum structure. Well, this happens especially in a steel structure. The steel structure had to be prepared, depending the duration of the force in relation with the period of the structure and the duration of the phenomenon to reach different values. So this is important to consider, especially when we design the connection. The connection has to be prepared to act in both directions. As another additional requirement, we have to consider also and to guarantee that this happen like this, to avoid the failure by shear, because remember that the failure by shear is fragile. I mean, the development is of displacement is lower than by bending. So this is important to consider, to take into account accurately this capacity of shear, also to avoid local buckling, and also to deal the joints between column and beam, like in a seismic design, and especially also in order to prevent lateral buckling of the beams or of the columns. The bracing is very important. This lateral bracing, or the wall that avoid don't reach a plastic hinge. For connection, the connection must be redundant and receive more than the member itself. So is you have to use connection, especially in facade or in the bottom, that avoid any brittle breakers, and especially a local, especially in the dealing with the facade, dealing with the roof. Usually the section fail by mean the so-called pull through. They remain in the purlin by the slab suffer from a sort of punching. It is also important to consider all this formulation about local and joints is based in the last resistant tension, and unfortunately in this parameter we haven't the same proportion that than for the GL point. Another point is relating the concrete, that we have an increasement due to the velocity and the dynamic load, and we have this dynamic increase factor that are taken for the first references. This is very important to calculate with these values, but this increase all the characteristic of the bending. The shear forces INC is the sort of Achilles heel, is the weak point. So it's an advantage to have 45 bar deformed or double resistant to the stirrups, in every section, in order to achieve a good connection, a good connection between reinforcement, and to enlarge the local capacity of the concrete. The limit deformation criteria in concrete is like this, in these references. Depending of category 1 or 2, we have this type of deformation, 2 degrees and 4 degrees. Well, this we will see afterwards, depend especially on how is the arrangement of the stirrups, and it's very advantageous to have a curve stirrup like this in this part, a sort of lacing. We will see this table is a consequence more or less. It includes also steel and concrete, and we have this value for different categories, like in the precedent table. And well, another point is this note, the note 3, the ductility radio depend of the relation between the reinforcement in the tension and in the compression part. But the maximum in beams is 10. But this achieve this directly when we have a symmetric reinforcement. Every side have the same reinforcement, the same number and diameter of bar. This is very useful, very educational figure. This is the behavior of the resistance of a concrete section, and this is the deflection. We can reach at last more or less 12. Usually the the failure has suffered before due to other elements, but consider that without any shear reinforcement, we only can reach 2 degrees, and we depending on the treatment of the shear, we can reach more value, more important. So of course, here is an advice is to design symmetrically, enabling the up and the bottom must be the same. Another advice is to use lacing or bars 45 degree in order to resist the maximum shear. So in this sense, it's very useful the composite section where we have the shear that act directly above the steel beam, and this is another table for the formation limits in explosive loading. It's a general. An advantage here is very useful this relation between the formation and span. You can see this support the conventional value we use in conventional design. A part of this that is about the frames and the general structure is very important to consider the facade. This is the distribution of pressure in a facade when the point of detonation is 20 meters, very close. As you can see in the bottom, the pressure are not linear, is not proportional to the distance. This is the weak part. We have to the problematic part. We have to reinforce all this part of this facade, and it's not important the in the 7, in the 6, in the 7 level are not so important. Another point is that when the facade, the modules of facade disappear, the explosion came into the building and produce uplift pressure. Usually the slab are not prepared for this. So this is another is the same advice, to be prepared that the forces can change even in an slab, not only for vertical descendant, but also for ascending, for uplift. So in these commentaries, it's necessary to consider that the close, the inner cores, the interior part, when we situate the elevator of the scales and play usually the role of stabilizing the building, is the more vulnerable. This must be is an issue to be protected, and it's important to situate just in the middle. Concerning windows and glasses face in the weak part and unconventional building, but in this sort of building there are a lot of material, special glass you can use according to this standard. In the reference one, there are a very useful collection of different glasses, the thickness of the glasses and different dimension in order to calculate the maximum pressure. They take into account the working as membrane, because it's not only a plate, and this is a good contribution to the stiffness. These are calculated, but in many cases are taken from the results are taken from a test. Another point is the debrief projection. Fortunately, when an explosion occurs, there are many elements that can be converted into projectiles. baskets, balls, boiler, benches, a lot of things are the primary elements. So surrounded building, we had to avoid these sorts of things. And well, on the other hand, sometimes there are secondary elements that are part of the building. So we deal with in the first part of this lesson to avoid complicated and sophisticated facades or element of facilities that in the facade. It's important. It's very useful to reach this publication. The FEMA, the FEMI publication is about safety, structural in general, and have a lot of publication against fire, against seismic, earthquake. I mean, one is just for this, for terrorist attacks, because sometimes the explosion is very close and it can affect an unconventional building. So, summarizing this master, we have to take into account a sort of a step, and well, the first is for an ordinary building to design for conventional load and to cope with the limited state and ultimate limited state. I mean to cope with to fulfill the law and the standard. Once we have this tax, then the second is to consider the earthquake. They consider the accidental load. The second is to consider, in that case, the explosion. But I would say that it's impossible to construct against the unaccidental action, no matter what is the nature of the action, if you don't respect the conventional design. So the first, concerning our subject, the first step is an idealization and simplification of the load. We treat this in the first part of this master lesson. So the resume is to obtain a simplified triangular load, a peak, and a duration, and well, and a momentum. So the second is a characterization of the structure. Obtaining different the mass and stiffness, and to consider and to take from this the period, and to compare the to compare this duration with the period, and to compare this maximum displacement that we reach by direct formulas or by the graphic, and to be sure that we are in within limit of the utility that cope with the standard. So well, don't forget, I was forgetting just the normal situation, the laws that are simultaneous and happen, and sometimes can reduce the margin of safety. So this is why when we deal with an specific project, is very useful to construct as light as possible. And well, consider that the explosion in that case is not coincidental with an earthquake or a maximum wind. Well, in case of the verification is not fulfilled means that we haven't enough ductility, but at the end, this is the most important thing. This value 10 or 20 or 5 or for some structures in nuclear power plant the response must be linear. I mean, if you not fulfill, the question is to change the structure. Usually is for to have more margin to analyze the weak points, because by means of this diagram, by means we diagram we show before, we can capture which is the weak point, and to reinforce only the point that don't fulfill the limits. I mean, is to perform a sort of this. Well, I found difficulty to find out who it was at the beginning. Let me see. Here is to have which is the weak point, and to make a correction of this. So when we cope with the main structure, and we consider the possibility in secondary structure, and we accept sometimes there are different limit of allowable ductility, then we can accept the design. In the final of analyzing this lesson, we have to show an exercise we made in another master. This is the structure of a slab in a roof, a slab made of concrete with one special reinforcement, and due to for shear and for flexure, we have a linear behavior until we reach the maximum linear. We have a second when the due to the lines of the Hinges line of the structure, the theory of plasticity, we reach this maximum, and this is a linearization of this. This coefficient can be obtained of the graphic, the annex, that is in the first references. These three. Another very important is the A. Well, of this bibliography is, of course, is useful, but I recommend especially this for this blast protection of building, and a standard just let me see. I can find now. Yes, was a part of this introduction of structural diagram. Realize the number of this edition. This is really, believe me, a sort of Bible. Not only for the knowledge of the background that it has, also for the clear concept that it has. In my opinion, no any other book has superseded this one. And here I add the coefficients for this part of beam. This is the equivalent, the maximum resistance, the equivalent stiffness, and this is the reaction. For instance, I will try to focus on this. And the reaction of the streams of webbing is a part of the maximum. I mean, is a part of the force. I mean, it's not just the equilibrium, the static equilibrium, but some part is due to the dynamic equilibrium. And I think this is all. Thank you very much for your attention, and I am at your disposal for any question.